Welcome back to JEE Maths Unlocked. Today we're looking at an elegant geometry question. How many normals can be drawn from a given point to the standard parabola y squared equals 4ax? Let's find out. We start with the parametric equations of the parabola. X equals at squared and y equals 2at. The equation of the normal at parameter t becomes y equals minus tx plus 2at plus at cubed. Now, if a point, h, k, lies on this normal, we plug x equals h, y equals k into the equation. Rearranging gives us a cubic equation in t. At cubed plus 2a minus h, t minus k equals 0. Now, the equation we obtained is cubic in t, which means that from any point in the plane, at most three normals can be drawn to the parabola. Let's denote its roots by t1, t2, t3. Each root corresponds to a point on the parabola where one of these normals touches. From the theory of equations, we know that for the cubic the following relations hold. To find how many normals are actually drawn from a specific point, we just count the number of real roots of the cubic. There are four possibilities. Case 1. 3 distinct real roots, 3 distinct points on the parabola, so 3 visible normals. Case 2. 3 real roots, but 2 coincide, still 3 normals algebraically, but only 2 distinct normals are visible. Case 3. All 3 roots identical, only 1 normal is visible, counted 3 times. Case 4. 1 real root and 2 non-real complex conjugates, only 1 real normal exists and is visible. Now, let's discuss each case in detail and try to find the locus of the point, h, k. Case 1. 3 distinct real roots. Let our cubic equation be f of t equals at cubed plus 2a minus h into t minus k. For a cubic to have 3 distinct real roots, 2 conditions must be met. 1. The derivative f of t must have 2 distinct real roots, say k1 and k2. 2. The cubic must take opposite signs at these 2 points, that is, f of k1 into f of k2 must be less than 0. This sign change criterion ensures that the graph of f of t crosses the t-axis 3 times, giving 3 distinct real solutions, and hence 3 visible normals. Now let's evaluate. We get this. Therefore, the criterion for 3 distinct normals is x greater than 2a and 27a times y squared is less than 4 times x minus 2a cubed. Now let's move to case 2. For a cubic to have 2 repeated real roots and 1 distinct real root, the turning points, given by the roots k1 and k2 of f dash of t equals 0, must satisfy the condition f of k1 into f of k2 equals 0. This means that the cubic's graph just touches the t-axis at one of its stationary. After evaluating, we get 27a times y squared is equal to 4 times x minus 2a cubed, and x greater than 2a. Case 3. All roots are real and identical, which means if t1 equals t2 equals t3, then from the sum of roots relation it follows that t1 equals t2 equals t3 equals 0. Substituting these values into the other relations, we get h equals 2a, and k equals 0. Therefore, the only point that produces a triple root, and hence only one normal counted 3 times, is 2a, 0, which is exactly the cusp of the evolute. Case 4. 1 real root and 2 complex conjugates. In this case, the cubic has no sign change between the turning points. Either the derivative has no real roots at all, or the stationary values have the same sign, which means f of k1 into f of k2 greater than 0 or the turning points are non-existent. Geometrically, this means there is only one visible normal from the given point to the parabola. We can actually evaluate the locus for this case using the same calculation as in case 1. The expressions for f of k1 and f of k2 are identical. The only difference is that instead of a less than sign, we now have a greater than sign. So, the locus for case 4 is x greater than 2a and in 27a times y squared is greater than 4 times x minus 2a cubed. Together with all points for which x less than 2a, since in that region the cubic has no turning points and hence only one real root. Finally, we bring everything together by plotting the curves for all cases on the same diagram. We draw the parabola and its evolute, then shade the regions corresponding to each case. Blue for 3 distinct normals, green for 2 visible normals, red for the unique cusp point with a triple identical normals, and dashed line curve for only one real normal. This consolidated plot gives a complete visual map of how the number of normals varies across the plane. And that wraps up our journey, from deriving the cubic for normals, to classifying every case, and finally mapping all the curves on one clean diagram. If this helped you see the parabola in a new light, don't just slip away quietly. Smash that like button, subscribe to the channel, and share this video with your friends so they can learn too. Knowledge grows best when it's shared.